Okay, this is your stats sensei, Mr. Spencer. Good morning, and we're going to talk about chi-squared test of independence, but we're going to start off with a quick review of independence, and this will probably take a couple minutes, and then we'll actually run a chi-squared test of independence. So independent events that do not rely on another. Please remember, if events are independent, the probability of A and B will equal the probability of A times B. So the intersection will equals A times B. Remember, independent events are not associated. They're not correlated. They're not related. And basically, we just stated the multiplication principle. And the multiplication principle says, if two events are independent, their probabilities can be multiplied to find the likelihood that the events will occur at the same time. So in other words, the intersection will equal A times B. All right. Remember, graphically, the corresponding segments will be the same size. All right. They'll be proportional. All right. They'll have the same proportion. So here's a 2011 question 2 problem. The table below shows the political party registration by gender of all 500 registered voters in Franklin Township. So we have 500. And we have 88 belonging to Party W, 244 belonging to Party X, and 168 belonging to Party Y. And then, of course, we have the breakdowns based on gender as well. So this is Part B. Among the registered voters of Franklin Township are the events is a male and is registered for Party Y independent. Well, I can check that by going, you know what? Probability of X and Y, or probability of male and Y would equal the probability of male times the probability of Y if they're independent. So in this case, 200 out of 500 are male, and 168 out of 500 belong to Party Y. So when I multiply that out, I end up getting 0.1344. However, there's my intersection. My intersection is 48 out of 500, and 0.1344 does not equal 48 over 500. So because it's not equal, they're not independent, all right? The next thing says, in Lawrence Township, the proportions of all registered voters for parties W, X, and Y are the same as for Franklin. All right. And party registration is independent of gender. Complete the graph below to show the distributions of party registration by gender in Lawrence County. Well, first off, what is the party registration in Franklin? Well, 88 out of 500. So 88 out of 500 is 0.176. So 0.176 belong to Party W. Party X would be 244 out of 500, or 0.488, or 48.8%. And then finally, we have 168 out of 500, which is 0.336, or 33%. And so this would be the layout for, this would be 0.176 right here. This would be 0.488. And this right here is 0.336. And because gender doesn't matter, they're independent, the male and the female would have exactly the same distribution. All right, they'd have exactly the same distribution. So that's what it shows there. Okay, continuing on. So suppose a speeding violation in the last year and B equals a car. So A is a speeding violation and B is a car phone user. A and B are independent. Then we can say by the multiplication rule, A and B equals A times B. All right. And A and B, or A intersect B, is the event that a driver received a speeding violation last year and is also a car phone user. So we have this table, and the table is only partially completed. We have 70 who received a speeding ticket, and we had 685 who did not. That's out of 755. 450, no car phone, 305 with a car phone, everything sums up. But they told me they were independent, and if I had to fill out the table, I could go 305 times 70 divided by this would give me that value. That would be my expected value, 28.28. And I'm going to go ahead and leave it as a decimal because that's what I'm expecting. Then for no ticket, 305 times 685 divided by 755 is this value. 450 times 70 divided by this will give me that. And then 450 times 685 divided by this will give me that. So that gets me my expected value. So that's where they came from, okay? So chi-square test of independence. The chi-square test of independence is a hypothesis test used to determine whether two factors are independent or not. Okay, we're going to say that there is whether there's an association or not. All right, and so there's a couple ways to write the null and alternative hypothesis, and they need to be written in sentences. All right, so, and like all chi-square tests, the test of independence will always be right-tailed. Okay, so first off, the blank and blank values are independent. The blank and blank values are not independent. And I always want you to write it like this. But please remember, this is saying the same as saying not associated. And this is saying the same as saying associated. So if they are independent, they're not associated, they're not related. If they're not independent, they are associated and they are related, all right? Please remember degrees of freedom. This is different than the goodness of fit. Goodness of fit was categories -1. Degrees of freedom for a test of independence is row -1 times column -1, all right? The rows -1 times the column -1. So up here, we had 1, 2, 3, 4, we had two, well, I should say it this way. We had 2 rows and we had 2 columns. So it would have been 2 minus 1 times 2 minus 1, which equals 1. So the degrees of freedom for this would have been 1 degree of freedom. Okay. All right. So like in a goodness of fit, you start off by goodness of fit, you're going to start off by writing your null and alternative. The conditions, random sample, n is less than 10%. This is really important on this. To be a test of independence, it needs to be one sample with 2 variables. And once again, here are our keywords: independence, association, and relation. Generally speaking, if those are the words, it's going to be a test of chi-square test of independence. All right. It's observed minus expected squared over expected. And we're going to have to go to the matrix function on the calculator. And this will be a little bit new, but it's absolutely fantastic. Okay. I think you'll end up liking it a lot once you actually use it. So instead of going and reading all this to you, I'm going to let you read it and then watch me do it on the example. And then our p-value is whatever. We reject the null. There is sufficient at alpha equal to suggest that they are not independent. If we're rejecting, they're not independent. If we're failing to reject, we're saying that they are independent. All right. So here we go. In a volunteer group, this is scenario 1. In a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recruits among community college students, four-year college students, and non-students. The following table is a random sample, so this is a single sample of the adult volunteers and the number of hours they work per week, okay? Are the number of hours volunteered independent of the type of volunteer? So in this particular case, first off, I have the part that I highlighted represents my data. I ignored my column totals, and I have 1, 2, 3 columns and 1, 2, 3 rows. So if I were talking about my degrees of freedom, I'd be going 3 minus 1 times 3 minus 1 would be my degrees of freedom, which in this case would be 4. They want to know if they're independent or not. Well, I'm going to need to calculate the expected values, and we can calculate them by hand. We can go 298 times 255 divided by 839. We can do that. Well, that would be pretty time consuming, okay? So, and then I can do for this one, 298 times 290 divided by 839, 298 times 294 divided by 839. But there's a much quicker way to do that. I'll show you in a moment. But let's start with our going through our recipe. The first thing, write our null and alternative. The number of hours worked and the type of volunteer are independent. The number of hours worked and the type of volunteer are not independent. Random sample that was given. The expected values are greater than 5. We look at the table and they are. Of course, we had to fill that in yet. We need to do the n is less than 10%. All right. And so we end up with a sample size of 21 adults. And we know that there's more than 210. So n is less than 10%. So 21 divided by 0.10 equals 210. Reasonable to assume that there's more than 210 people volunteering hours. All right. And the counted data. So how in the world do I fill in that table? Because that's really important because we're going to have to do that. So here's what we do. And this will take a little bit of time. So here's how you get there. Second, followed by matrix. Oops. Try that again. Second, followed by the matrix button, which is right here. You're going to arrow over the word edit. Well, we have a 3 by 3, 1, 2, 3, 1, 2, 3. Remember, it's rows times columns. So 3 enter and 3 enter. And then I need to enter my data. So I'm going to go 111, then 96, 48. And then it automatically drops down and 91 enter, 133 enter, 61 enter, and et cetera, et cetera. Now I messed up my data here, so I need to fix that. That's 96. Enter, 133 enter. I'm having trouble. 133 enter. There we go. 61 enter, 91 enter, 150 enter, 53 enter. So all the data is now entered, and I can go ahead and quit out of that. So second, quit. So we're out of that. We're going to go stat test, and we're going to go ahead and run the test. I know that seems a little bit counterintuitive, but we need to do it. And we're going to take, in this case, we're just looking for a chi-squared test because it's not the goodness of fit. It's just a chi-squared, plain old chi-squared, letter C. Observed is an A, expected is an B, and I know you haven't done the expected, but you're going to have to trust me for a moment. Calculate, and we get a chi-squared value of 12.99 and 0.011 is our p-value. Let's go ahead and write that down because that's going to be important. We're going to want that. So our chi-squared equals 12.99. And our p-value is 0.011. All right, so I need to go back and figure out my expected value. Here's how you do that. So we're going to go back to the second matrix. So second to the matrix button, which is right here. We're going to go arrow over to edit. Having a lot of problems with the light today. Arrow over to edit. And then I'm going to drop down to B. We entered everything into B, but B all of a sudden shows up. I press enter, and there's all my expected values. It's calculated them all out for us. All we need to do is write them in the table. Normally on the AP exam, they'll give you enough space and you can write it next to it. You won't have to make a separate table. Okay. All right. So I now have all my data. So I can do an observed, which was 111 minus my expected, which is 90.572 over this, plus dot, dot, dot. Then we expected 53. That was the last one. Minus this, the 53 minus the, makes it, we observed 53, and we expected 56.7. So 53 minus 56.7 over 56.7 equaled the p-value of 12.99. I mean, the chi-squared of 12.99 and the p-value of 0.0113. All right. So our p-value is about 0.011, which is less than 0.05. So we reject the null. There's sufficient evidence that alpha equal 0.05 to suggest the number of hours worked and the type of volunteer are not independent. All right, because we rejected the R independent and we now accepted this. Conclusion, the number of hours worked and type of volunteer are associated or are related. All right. So that's scenario 1 for chi-square test of independence. You may want to watch the next video because it takes a little practice on the calculator, but I appreciate you joining. See you on the next one.